One of the first things when it comes to people's mind when we talk about packed bed assertion column is pressure drop, because when a convective flow of material or gaseous stream happens across packed bed, obviously there's going to be pressure drop due to the loss in the momentum, right? And momentum balance is required. And the flow is largely driven by the difference in pressure in this case, right? Flow of the material happens from the higher pressure to the lower pressure. So momentum balance is a crucial component of complementing the energy balance and the mass balance equations that we've driven. So we need to be able to write these momentum balance equations. One of the hallmark equation is the standard Argon equation, which relates the volumetric flow rate to the pressure gradient at each point in the absorber. So we just have to discretize this Argon equation, which is written in terms of the partial differential equations, dp dg, right? And then we're just discretizing it and doing bunch of algebra, right? And of course we're treating this with the treating these so that these flow rates are numerically robust, right? So we do some transformation so that the final form of equation is just explicit, right? So the volumetric flow rate in the nth stream is basically written as an explicit function of these terms, which is numerically stable, right? And similar derivation, right? So instead of when we remove the quadratic term from equation 20 and do the derivation, we get the Koženik-Harman equation, which ends up writing the linear difference between the two adjacent CSTRs is directly proportional. The volumetric flow is directly proportional to the linear difference in the pressure in the two adjacent CSTRs. So these are the two different equations, and notice that we don't really need to calculate the pseudo-volumetric flow rate in this case. However, since our model is written in terms of pseudo-volumetric flow rate, all we need to do is actually go back and just plug in these calculated volumetric flow rates into the definition of pseudo-volumetric flow rates, and then plug these into the mass and energy balance equations. So again, the unknowns are the volumetric flow rates between the CSTRs. So basically, even after writing energy and mass balance equations, we need to specify these volumetric flow rates above and below different CSTRs for all CSTRs. So what we're doing with this momentum balance equation is trying to derive those expressions just to get those volumetric flow rates. And this paradigm of using momentum balance equation is called pressure-driven simulation.